Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapiens Education. I'm going to solve question number 9.11 for the chapter Mechanical Properties of the Fluids. So here, uh, the question is: can Bernoulli's equation be used to describe the flow of water through a rapid in a river? Let us assume that. What is the Bernoulli's equation? Condition for the Bernoulli's equation is condition Bernoulli's equation flow should be steady. Okay. Now, if there is a rapid flow, if flow is rapid in river, then the flow is non-steady, which means it can't be used. It can't be used. Okay. So why this happens? See, if there is a water is coming like this, water is coming like this, and making a coils and all. So only A1 B1 is equal to A2 B2. Continuity equation can be applicable, but Bernoulli's equation can't be applicable. Now, question 9.12: does it matter if one uses gauge instead of absolute pressure by applying a Bernoulli's equation? Explain. Now let us first of all write the Bernoulli's equation. So, but the Bernoulli's equation is that P plus OGH plus 1 by 2 V square is equal to constant. Now we know that gauge pressure is equal to absolute pressure the gauge pressure plus atmospheric pressure is equal to absolute pressure. So if we put here in place of a gauge pressure, in place of a actual pressure, so we have to put like this: P gauge plus P atmospheric pressure plus rho gh plus half rho v square is equal to constant. Now see here, this is a constant term, so we can also write P gauge plus rho gh plus half rho v square is equal to constant minus P atmospheric pressure. So this is also constant, this is also constant, so some new constant will be there. So P gauge plus rho gh plus half rho v square, so that is absolutely fine to use gauge pressure. Okay, but one thing may happen that here everywhere it is a positive, so addition of all positive will be positive, but in gauge pressure there may be a chance of negative, so maybe constant will be negative, but mostly we can use this thing. I hope you have understood this. See question number 9.13. It's a glycerin flows steadily through a horizontal tube length 1.5 meter and radius 1 centimeter. So let us make a tube. So let us consider there is a tube. okay, and its length is L, and let us consider its radius is R. Okay, the glycerin flow steadily means, let us consider this is the flow rate, Q is with which it is flowing. Now let we know that if the amount of glycerin collected per second at one end is 4.0 into 10 power minus 3 kg per second. So mass m dot, that is mass flow rate, they have given mass flow rate, that is 4.0 into 10 to the power minus 3 kg per second. What is the pressure difference between the two ends? So we require to find delta P. Okay, so as you know that the formula Q, that is volumetric flow rate. Q is your volumetric flow rate, it is not a mass flow rate, it is volumetric flow rate. So Q is dot is equal to pi into R to the power 4 by 8 into eta into L to delta P. So we require this change in a pressure. So before that we have to find Q. So since we know that mass flow rate is given, so first of all we know that V, that is volume is equal to mass by density. So if we differentiate that is dV by dt, so this is volumetric flow rate and this can be written as Q, and this is equal to dm by dt into 1 by density. So dm by dt is only mass flow rate they have given. So from here mass flow rate, from here Q can be written as mass flow rate, that is equal to 4 into 10 to the power minus 3 kg per second divided by density. So density of the glycerin they have provided 1.3 into 10 to the power cube. So when our answer, so answer will be 3.08 into 10 to the power minus 6 meter cube per second. Okay, now if we want to find delta P, so from here if we want to find delta P, so delta P can be written as, if we delta P, we need to find a delta P. So if we want to find a delta P, so if we want to rearrange the equation, so delta P will be equal to Q into 8 into eta L divided by pi into R to the power 4. So Q we have got 3.08 into 10 to the power minus 6 meter cube per second. So we are taking as a SI unit. What is the value of eta? So we have a eta that is viscosity. So it is viscosity of glycerin is 0.83 Pascal per second. So let us consider this 0.83 Pascal per second into length. So length of the pipe, they have given length of the pipe is 1.5 meter. So by this divided by pi into radius. So radius is 1 centimeter. So convert it into meter. So this will be 10 to the power minus 2 to the power 4. So when we collectively find this, so we will get a change in pressure, that is delta P is equal to 976 Pascal. Okay, so this is the change in a pressure will be happen if it will flow from this. So there is a flow. So there is, let us consider there is P1 and there is P2. So whenever there is a difference in a pressure, that is P1 minus P2, then only there will be a flow happens. Okay, now the another part they have also given us that we can round up also this as a 980 Pascal. Now they are also you may also like to check if the assumption of the laminar flow in the tube is correct or not. So is it laminar flow or not, we need to find. So you know that we have a Reynolds number. So Reynolds number Re. So Re is equal to Re is equal to rho into velocity into T by N. This is the diameter. So velocity, how you will find velocity? So first, see, rho density is given, diameter is given, viscosity is given. So first of all, we need to find a velocity. So velocity, we know area into velocity is q flow rate. So from here, velocity is equal to q by area. So q we have got how much? We have got 3.08 into 10 to the power minus 6 divided by what is the area? So the area is 3.14 into 10 to the power minus 4, because it is r square, so radius is 10 to the power minus 2. So finally, if we get calculate it, so we will get 0.98 meter per second. So we have got velocity. Okay, this is velocity. Now we need to find Reynolds number. So Reynolds number will be equal to rho, that is density. So Reynolds number, that is density, that is 1.3 into 10 to the power 3 into 0.98 into 10 to the power minus 2 into 2. It is centimeter per second actually, velocity. So that's why I have converted into meter per second. And dense, d is the diameter. So diameter is 2 into 10 to the power minus 2 divided by let us do with this then next slide, so that so Re will be equal to see, let us put here 0.83. So Re will be equal to 3.07 into 10 power minus 1. So finally it will be 0.307 or 0.31. So Reynolds number. But for we know that for turbulent flow in tube, Re should be greater than 2000. Okay, so here, but here for laminar Re should be less than 2000. So here the flow is, hence it is the value of Reynolds number is 0.31, which is less than 2000. So hence it is laminar flow. Okay, so I hope you have understood this. Experimental model aeroplane in a wind tunnel. The flow speed on the upper and lower surface of the wings are 70 and 63 meter per second respectively. What is the lift on the wing if the area is 2.5 meter? Take the density of the air to be 1.3 kg. So let us make an aeroplane wing. So let us consider this is the wing, and the upper has a velocity v1 is equal to 70 meter per second, and lower wing, that is velocity v2 is equal to 63 meter per second, okay, respectively. Now we can consider this as at the same height, so we can cancel out the potential energy. So let us we know that the equation for Bernoulli's equation is pressure plus half rho into v square plus rho gh is equal to constant. Now since it is also constant, so here we can write P plus 1 by 2 rho B square is equal to constant. See this. Now we can put here P1 plus 1 by 2 rho. Rho is common for both because it is same area into V2 V square is V1 square is equal to P2 plus 1 by 2 rho V2 square. Now we know that the velocity V1 is greater, so we can find like this: half rho V1 V1 square minus V2 square is equal to P2 minus P1, which is the pressure difference. Okay, so this is the pressure difference. So if you will calculate it, so the pressure difference is equal to 1 by 2 into rho. Rho is the density, so density of the air is given as 1.3 kg per meter cube into 70 square minus 63 square. So when we collectively calculate it, so we are getting a pressure difference of 0.605.15 Pascal. Now we have got the pressure difference. Now they are taking that they are telling that in a test, what is the lift? So lift means what is the force? So the force is equal to force of for lift is equal to change in pressure into area. So the change in pressure is 605.15 into area is how much? Area is 2.5 meter square. So when we get additionally collectively calculated, so getting up the number 1513 Newton, or if you want to find round off, so this will be 1500 Newton. So this is the force for the lift. I hope you have understood that due to velocity difference we have created a pressure difference, and due to pressure difference we can find the force on the lift. I hope you have understood this. Now let us do the next question. Yeah, this is very interesting question. In figure 9.20 refer to the steady flow of non-viscous fluid. It means that there will be an applicability of the Bernoulli's principle. The two figures is of the two figures, which of the figure is incorrect and why? See here there is a less area. In figure it has less area, so velocity will be high. As per the equation of continuity, suggests that a1 v1 is equal to a2 v2. So if velocity, if you talk about this area, so if this area is a1, the velocity is v1, so suddenly area a2 decreases, so velocity has to increase. So velocity v, let us assume that this is 1 and this is 2, so v2 velocity is greater than v1. Okay, now using this, so this is one condition, this is second condition. By using this, now we need to use the Bernoulli's principle. So Bernoulli's principle, we use that p plus rho gh plus 1 by 2 rho v square is equal to constant. Since it can be also constant, so p plus 1 by 2 rho v square is equal to constant. Why it is constant? Because it is at the same level. We can assume that it is at the same level. So p1 plus 1 by 2 rho v1 square is equal to p2 plus 1 by 2 rho v2 square. Now see here, if v2 is greater, it means that pressure has to be low. If v1 is less, so p2 is more. So from this equation we can infer that p2 is less than p1. So if p2 is less than p1, so what happened? If we see the diagram, so this is p1 and this is p2. So if pressure is less, so the less height it should be, the fluid lift of the fluid should be high in the capillary tube. But here in this lift of pressure p2 is very high, it means that it shows the high pressure, which is wrong. So finally we can come to the conclusion that the option B is the correct one. I hope you all have understood this. Oh, how many of them? Two people. Who?